Okay, so let's continue, please, with this model that we have. The aim of this, as I mentioned in the beginning, is to have the more fundamental idea of why we have bands. So here we're going to explore the band formation, right? So please come back to this notebook. Okay. So in my case, for instance, in your case, let's suppose that you open back this notebook after a week. So my suggestion is, first of all, evaluation. In my case, I quit kernel because I've been using Mathematica for this class. And after this, look what you do. Very simple. You go to the beginning of this, look, I collapse this, and after just I put shift enter here. And automatically will generate back everything. See? Okay, as you can see here. Right? So my kernel is uploading, so nothing, no worrying so far. And in a moment, we will start to generate this. All of this will be generated automatically till the last point. Okay, that's it. So this, with this, the last part here, remember, we want to study what happened with the level one. Remember, so we have this. So I'm going to draw here in the my white piece. So we have my potential here, right? And based on the parameters we have here, for this case, we have three energy levels. So I have one, two, and three. Three energy levels. Right now, what I want to, we already computed energy levels, but now I want to visualize the wave functions and also the probability density. Okay, so how to do this? Very simple. So let's start to generate this. Okay, so we have this, and now we have. I'm going to put like this, okay, because we are going to use to create the summary figure, right? N val. Remember, N val right now is take the value of one, so that's the reason take it blank. Is equal to plot. So we're going to plot this, okay? So we're going to plot, right? V of x, where I put always a small letter, no capital letter. This the energy, right? The energy. So I shift everything by the value of the energy plus 1 over rho squared of int. Remember, this is the normalization factor that I mentioned times value of x, see, comma, and this again here, right? This square. Why square directly? Because the wave function is real, so no problem. Square, right? Or if you like, you can put the square this phi conjugate times phi. This is the same. Okay. This I'm going to replace this. Sorry, I forgot to put after the plot. Please put this. Okay. Put this curly bracket here. This okay. And now I replace this, right? Alpha. So we don't have to do this because we have already this here. Please copy this here. You see? Copy this here. Look. And after also replace the other one, right? So I have this, this, and this. All this here. Okay. Comma. Now I'm going to give the domain from x from minus 2.5 to 2.5. Okay. Now plot range all. Access level. So this we are going to do this. We do once and that's it. X, that it will be in board. Remember, the units is in boards here because it is atomic units, is the board length, and the energy. The energy is given in matrix E sub H. No? Base style. So this is the form family. font size. I'm going to put comma, plot style. I'm going to put it like this. Red, so the potential will be red. Okay, that would be the color of potential. The energy will be orange. The wave function in blue and the probability density in green. So, comma, exclusions, none, comma. Filling, now we're going to fill in something here will be 1 to axis and 4 to alpha. So we want to do this. 4 is, it means that the probability densities will be n bar. And that's it. Let me see it works. Cross the fingers. Fantastic. Okay. So few things before recording. So this is the plot, as you can see here. And here, you can notice one detail. Look the wave function now. Compared with the previous case that was infinite potential. Well, you have, since not infinite, look this. The wave function of the probability of finding electron outside of the potential well is non-zero. You see? You see the tail here, the probability of finding here is not zero. So it means that the probability of finding electron outside of the well is not zero. How we call this? We call barrier penetration. Very important. Why happens this? Again, is because the wave nature of the electron, right? So the electron is not completely localized. Despite of the highest probability of finding electrons in the middle of the barrier, it doesn't mean that the electron cannot be found outside of this. Okay? So that's very important feature that we have from quantum mechanics, right? So this is a quantum behavior of this. So the first thing that we can check is right. So let's first of all, what is the integral of this 5x? So this is 5. What is the integral of 5 conjugate times 5 dx from minus infinity to infinity? What is this? Has to be 1. What does it mean again? It means that the probability of finding electron in any part of the space, not only inside of this, outside outside of the well, in all the space, has to be 1. It means that if you find the electron to be 100%, right, you are not going to find 0.1% of the electrons. That is not possible. So this is one of the things that you know the that we are forced to accept from the Copenhagen interpretation. So let's check this and integrate this, right? This would be 5, so will be this. I'm going to copy this. Please just copy this. 5 conjugate, right? Replacing. Okay, again, please copy this, placing this alpha and replacing this still here. Here, all of this. Please copy this. From the figure you have that, this, comma, from x minus infinity, escape in. Has to be the value, let's put like this, chop. See? So with this, we prove that, yeah, my wave function computed for this energy level is correct in the sense that we integrate this is fully normal. So the probability of finding electron in any part of the space has to be 1, right? So that makes sense. Otherwise, no, it's not possible to do this. So the first question is, for instance, what is the probability of finding one electron one electron within minus A over 2, this within this region, right? Minus A over 2, less or equal x in this region, A over 2. What is the probability of finding this in this region? How to compute this? Please copy this again, paste it, and now we're going to find from minus A over 2, so will be from minus L A over 2 to LA over 2. So the probability is 0.97. So it's 97% probability of termination inside of the well. You see? Very interesting. It's not 100%. Why? Because there is this so-called barrier penetration. Okay? The question is now, what is the probability? Copy this, please. Yeah. The probability of finding one electron outside, for x of x more or equal to more than A over 2. What is the probability? Find outside in the right branch, let's say this part is on the right side here. So we wanted to know what is the probability of finding electron in this region, of this. So how to do it? You can predict how to do it. This will be from 0 from L over 2 till infinity. Okay. So that's the probability of finding electron on the right side of the potential here. And what will be the probability of finding electron either here and here? Will be 2 times this value, right? Fine. So what's the final electron outside of the well will be 2 times the value we copy there. Or you just add this integral from minus infinity to minus LA over 2 plus this integral, right? So that will be the probability. Now let's find the uncertainty. We call uncertainty in physics delta x, right? That is the standard deviation of the position, right? For one electron, in this energy level. Okay, how to do this? First of all, we have to compute. Remember, what is this value? What was this the expected value? Remember, first of all, what is this delta x? It is equal to rho square of the expected value of x squared minus the expected value of the square of the mean value, right? So what is this, please, buddy? Remember?
The one in the next. Yes.
Right? Anthony, what is this? The expected value of x squared. So conjugate times x squared times 5dx, right? In general, that is the observable, right? So the observable every time quantity, let's say Q, is equal to the integral minus infinity of phi conjugate times the operator times 5dx. In quantum mechanics, the operator x goes to x, the operator p, right? The operator p in quantum mechanics is
And there will be perspectives.
don't forget that, right? So in quantum mechanics, the operator p goes like this in, the space. Okay. Okay, so let's compute please so what is the expected value of x? How to do this? So expected value of x. So let's compute very quickly. So to put this, how to put this, please remember that this is escape minus escape. And this is, we're going to make escape minus escape. So let's put escape, escape, that is equal to, and I'm going to copy this, please look this, I'm going to copy from here, this one. I'm going to copy this, please, and paste it here. I'm going to do this. The only thing I have to put here between these two is, that's it, right? Nothing else. You see, is the conjugate of the wave function normalized times conjugate, right? Times the x times this, from minus infinity to infinity. So the expected value is 7. So the expected value of the position x is, why is 0? Because look, if my system is symmetric. The system is symmetric, that is. You see the potential. That is the say over 2 to the over 2. You see, the potential is symmetric. That's the reason why we have this. If we shift, Lucas, if we shift the potential, let's suppose if you move this potential here, that is around x0, let's say, the expected value of this will be x0. So this is a typical, for instance, I know some of you are going to give some exam in GRE, and it's going to give you, no, give me what is the expected value of these things. Just for information, right? This case, in this case, it will tell you. X and this is the entropy, right? So what will be? Is this exactly X also? Just simply. Because it's, it's symmetrical with respect to these points. But you see the physics of that's not changing by shift with moving. Okay. And at the end, what is important here is this. So in statistics we call this the standard deviation. In physics we call the uncertainty, right? Remember when you did experiments, you were asked to find this, some value, let's say value, I don't know, some value quantity, let's say V0, plus less something, right? Delta V. So this is the uncertainty. Remember this when you did the experiment, maybe tronco común, you were asked to find this plus less what value. This is uncertainty. This is exactly the same value we're going to do. Okay. So what is this? Who can tell me, Edward? What is now the we have this? What is this? I copy. You see, I copy paste and just this x square and this. Piece of cake. This will be x squared. What is the value? Is 0? No, it's not 0. 0.23. Okay. So this the expected value of x squared is not 7. It is 0.22. Okay. So we have this. Then delta x is, what is delta x, please? I'm going to delta x, k capital D, escape D, x equal to control 2. This, it's very simple. You just copy this, minus this square. What is the uncertainty of the position? Is 0.47. Remember, this is atomic units. Atomic units. That is the uncertainty on the position. Let's please questions here, somebody, please? Okay, so now we are going to find the uncertainty delta P. What is this? To compute this, just very simple. We're going to use this one here. Going to Control C, P, and after I'm going to change this to P, this. So we did this, and instead of this X, I'm going to put one parenthesis here. Sorry, I'm going to cover it with two parentheses here, this and this. And this, I'm going to use this. Here inside, I'm going to put minus I is times the partial derivative is d, the parenthesis, close parenthesis, okay, of what? Of this function, right? Isn't it? Right? Comma, 5x, comma, in x. So this is exactly the minus I, the partial derivative with respect to x for this function. Then you do the same operation from minus infinity to infinity, and the answer is 0. Right? So don't forget to save. And now we need to find this, the expected value of p squared. What is the expected value of p squared, Angel? Minus infinity to infinity of sine 4 of p. What is p squared? If p in atomic units, is p equals like this, okay? Right? Minus 9 px. What will be p squared, please? Angel?
The derivative is from the variable.
Right? This is equal to minus second derivative dx in atomic units. In the unit, no, in other units will be h bar is minus h bar squared. Right? So the p square, I'm going to copy this, please. Paste it here. So p square, please, will be this, right? Minus the second derivative will be like this. How to put the second derivative? We put like this here. This is the second derivative of my wave function with respect to x. Minus because we have this from this result. Given like this. Remember that is in atomic units. Then the uncertainty momentum is this, right? This, I'm going to copy this one here, here. So like this, I change this. And I change P instead of X. It's like this, 1.075. Okay. Okay. So now then, we have this. Therefore, I'm going to put the text here. Therefore, the Heisenberg uncertainty, the Heisenberg uncertainty principle that says that the uncertainty position multiplied by uncertainty of the momentum is more or equal than h bar over 2, right? We have this from Heisenberg uncertainty. In atomic units, h bar is 1, so in atomic units we get more or equal than 1. Sorry, 1 over 2. 0.5 if you like, 1 over 2. So we have to look at this. So let's see if this is correct. So what is delta? That's the position on the momentum. You see, it is 0.51. So it means that we are not violating a very fundamental property of any kind of system of this, right? So if you find somehow in your experiments or in theory that is less than 0.5 in the units, there's either you did something wrong or you find something absolutely present, right? Believe it or not, many experimental groups always try to check for properties. And so far, never been seen. So far, we haven't seen any violations to this. Okay, we have this. Now the next question is what is the expected kinetic energy? What will be the expected kinetic energy for one electron? An electron, right? Is energy level. What will be? What will be the expected kinetic energy? What is the? You can tell me what is the dynamic? What is the kinetic energy operator? Remember, in classical mechanics, what was kinetic energy? As a function of momentum. E squared over 2. Right? That is the over 2n. That is the kinetic energy classical mechanics. In quantum, we already quantum K, we just put the heads. Right? So what is P squared in atomic, sorry, if we go in atomic units, well, this is will be like this. Is equal to P, to be this. The square would be this, right? P is minus I, H bar, that's the to X, multiplied by the same, that is P squared. Right? Divided by 2n. So this the kinetic energy operator would be plus I squared is minus H bar square of 2n set of derivative respect to the x. In atomic units will be the same, but remember H bar is 1 and n is 1, so you just 1 by 1 to the second derivative to the x. That is the kinetic energy operator. So what will be the expected kinetic energy, please? Will be the integral minus infinity to infinity of sine conjugate. Right? Multiply by this minus 1 over 2, the second derivative of the x squared by the x. That's it. That's it. The kinetic energy. So let's compute this. So K-val, so I'm going to put like this, please. Escape. So let's copy better. Let's copy this. To do this, let's copy from the momentum, from this. Copy this, please. From P squared, right? So I copy this and I change this. Please change this from like this. Small k sub control minus n val. Okay? Let's try to go like this. K sub n val, please. Let's put that. And this is integral to this minus 1 over 2, you see? The second derivative, right? The second derivative is exactly the same and that's it. So the kinetic energy is this in atomic units. So it will be in hertz, this energy. Try to put like this in K sub 1. Okay. And again, what is the, sorry. What is the expected potential energy for one electron in this energy level? This energy level. What is this? I'm going to please copy this again, this from this part. Paste it here. Instead of K, you are going to put U. And what will be? Instead of all of this, you are going to just erase this. We are going to keep only this, please. To erase all of this here. And you're going to put B of X multiplied by this. That is the expected kinetic energy, the potential energy. See? So I erase, as you can see, I erase everything and I put this B of X because the potential was already defined. And I put this back, this will normalize with. That's it. So the potential is 0.7. Okay. Now let's check what is the, so what will be the expected value what is the expected value of the Hamiltonian, and we call that the energy of the system. What is this? It's just, is this, right? The kinetic energy plus the potential energy. Let's see. Therefore, now let's check this. Please check this. So what is U val? Look this, I'm going to copy this, K val plus, so if I add these two, I have to have exactly the total energy in my system. That, look this, this is the, total energy that is, it has to be exactly this, right? Replacing K val with this. See? It's exactly the same. Control this. See?
Well, that's just to show you that everything has to be merged, right? So if you assume the expected value of the kinetic energy plus the masses plus the expected value of the potential energy, you have to have this one. That is exactly the HMI.
Don't forget to save it. You remember, I recommend these notes is yours, your notes, but you, right now you can write here some notes, that's something that makes it clear, realize you can put this for your future. Check. Okay. It'll be good notebook for future study. Okay, save it, please. Any questions to hear somebody, please, before I go? Now we are going to fly because you have already all. Okay, so we spend all this time because of this, please. Sorry. Because of this, I'm going to put this. I'm going to collapse this, and look this. I am going to collapse all this. I'm going to copy this. Paste it here. Change, please, level 2. And now just change only this parameter. This parameter change everything. Now collapse this again and shift enter, and you're going to have everything but for the level 2. I repeat again, please. No worries. So since if you check everything is fine, there is no errors or whatever. So I collapse this, please. Collapse this. I copy the whole part here, you see. Here I can you just select this part here, Control C, paste it here, press Control V, change this to level 2. Change this list. And after this is the only thing you have to change. After that, collapse this again, or just select everything here, Shift Enter. That's it. You're going to check everything makes sense in the values, you see. Look with the barrier penetration. The higher the energy level, you see the probability to find the electron outside of the well is also higher, right? You see, start to increase here. So here's the expected values. You see the Heisenberg uncertainty, please. Now is the 2.05 and so. Okay. And let's do this since there are 3 energy levels. Let's do for the third energy level, level 3. You just change this 3 and shift enter. And there it is. We have even for the third energy level. Okay, Control S, and I'll wait here till everyone has exactly the same. So now I'm going to put a subsection, a summary of the plots. Yes, I'm going to put this as a subsection. Summary of the plots. And here just put this show table figure I I. Okay. Yes. Now I'm going to pause this here. So please, here, after you do this summary of the plots, here you're going to see that the wave functions here, there is no nodes in level 1. So we call sometimes this S orbital. One node here, you see, is S, the p orbital, and two nodes is d orbital like orbital, right? Other thing is that you have to remember that here, when, for instance, the p orbital here, the probability of finding electron exactly in the middle is 0. So you may think, how is that possible? Since the electron is moving all this, how is that possible? Not possible. How is that possible that you will never find an electron through this point? It's because of the wave behavior electron. There is a canceling of between waves. That's the reason why we have this kind of properties. This is a wave behavior for the electron, right? So now let me see, please. Let me see if you understand. So let's ask this. What is the total energy of the system? What is the total electronic energy of the system if this atom has, for instance, 5 electrons? What will be it? Somebody can tell me this. What would be the total energy of the system if the atom has 5 electrons? So, Buddy, how many? You have 5 electrons. How many electrons can you put here? 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 So please, what is the total energy of the system? How to compute the total energy? How to do it? Please. I'm going to pull this, Okay. That is equal to this. Basically, it's like this, 2 times the air valve, right? The air valve, because we have this I from 1 to 2. So will be air valve 2 times what air valve 1, air valve 2, 2, plus only 1 times air valve 3. See? So this will be the total energy of the total electronic energy of the system, right? Please tell me what is the total kinetic energy of the system? What is the total kinetic energy of the system with 5 electrons? What do you think will be? What would be the total kinetic energy? I'm going to put K sub dot. Yeah, right. So I'm going to put like this. No, let's put sum the sum again 2 times since we computed this sub I. See, we already computed this. Comma I, comma 2. So the K1, K sub 1, K sub plus K sub 3. See, that is the total kinetic. Remember, this is in Harkins. And what will be the total not kinetic now potential energy? What will be the total potential energy, please? Potential. What do you mean, please? We're going to put like this, exactly the same. Instead of put K dot, we are going to put U dot. U dot with this. Instead of K, is by U. That's it. See? And notice that, right? If you add this K dot plus Q dot, you have to have it at the total electronic energy. See? So some properties that You know already this, but just in case you forgot to do this. I know that you're okay. So I'm going to do now, we're going to do the case of three by the two atoms together. Okay. So I'm going to copy this, please. I'm going to put the two final or double final potential where model of a molecule, please. This is for a molecule. Okay. Model for a molecule. Look this how I'm going to add. First of all, to start again this, please erase everything but level one. And summary just erase this. Level one. Okay. So I'm going to leave only level one because we have to generate a proper level one, and after we will check how many levels. Okay. Let's define the potential. Look this. B0 now is between minus A over 2, oh, sorry, minus B over 2. So it's a minus A minus B over 2. See? 0, because you see, just copy this. You have to take your time not to make this. To B over 2. B0 in between B over 2. Right? Sorry, this to minus B over 2 here. Sorry. So this is my. The other one is from minus B over 2 less that B over 2. See? Control Enter, please. You see? With Control Enter, you are at here the last part, you put less Control Enter, and you get the same, the big sphere. 0 is when in between B over 2. Less or equal, x less or equal on A plus B over 2. And finally, Control Enter, B0 when x is bigger than A plus B over 2. Tell me. 1, 2, 3, okay, minus B over 2. Sorry, thank you, correct. Till B over 2, correct? B over 2, thank you. You see? And we are going to put like this. LA 2 words and LB, please, is going to be 1 word. You see? I just adapting from this. I just have to say what is B. LB will take the value of the length of B. So shift enter here, shift enter here, please. And now since we are going to use atomic units, so we're going to have like this. And now we are going to see this, right? We are going to replace this. LB is going to be LB. You see how this? And next is I'm going to put minus 3.5 to 3.5. The rest is exactly the same. Let me see it works. Fine. Okay, I'm going to pause here 1 moment. Now we are going to solve the Schrodinger equation, please. Okay, we are not going to use this, please, because we are going directly to this. Please erase everything here till here. See, we're going to erase this. And now we have to define how many wave functions, 1, 2, 3, 4, 5 wave functions. So the first wave function is going to be exactly the same here, The phi 1 and the phi sub 5 are going to be exactly the same for the sign. So we know already this. And in between these ones has to be described by linear combination of sinus cosine of plane wave, sinus cosine. This in between is a linear combination of exponents. That's it. Okay. So phi 1 is exactly the same. Phi 2 is exactly the same. Phi 3 will be this plus C5, look this, multiplied by the exponent of this. You see how it will start to do very quickly? Sorry. Of positive alpha x. Okay. Phi sub 4 x has to be the same as phi sub 3, as phi sub 2, sorry, with different constants. See, I copy paste it, And I say for this is 6, this is 7. See? And finally 5 to 5 of x, that is equal to this. I'm going to copy this, please, and change the sign here. So will be c sub 7, c sub 8 of minus 1x. And that's it. Don't forget to set. And now, remember, since the constants are going from 1 to 8, so you have to change this to 8, and the 5 goes from 9 to 5, please. You have to change these two numbers here to 8, to 5, this, look, this, and have this. Check that you have phi1, phi2, phi3, phi4, so 5, and you have c1, c2, c3, c4, c5, c6, c7, c6, c8. Shift enter. There it is. Okay. Okay. So now we have to continue. Let's define this. Look this. What I have to do is the following thing. Please copy the potential, please. Paste it here for the wave function. And you are going to change here to phi sub 1 of x, please. And after you copy this and paste in all this, copy this, Control C, and I paste it. And I change the subindex 2, 3, 4, and 5. And that's it. Shift enter. I have the wave function. The equations, please. Now the questions we have to take care. Okay. This is the questions we have to take care. This is minus a, sorry, minus b over 2. Please be careful with this. Or if you like, copy this and paste it here. You see, that's the reason we have this. The same here, please. You don't change anything here. Question 1. So because we are going to have in total, we are going to have 8 equations. So these equations, the only thing, the first 4 equations, you have to change only the boundary conditions here. Let's go to 3. The other one was here, right? See, in the state of this, a over 2, I put minus b over 2. B over 2. Okay. Next, equation 4. Equation 5, sorry. To this, I'm going to copy this, please. Paste it here, and I have 3 here. Set 2, 3, and 4, please, here. 4. And x is not minus b, is b over 2. See, b over 2. Yeah. And besides, and equation 6 will be exactly the same, but with the primes, please. Equation 6 will be 5 3 prime, 5 sub 4 prime. Okay. Equation 7. Please, I'm going to copy this, please. This is here, equation 5. I'm going to copy this. Here I have 5 sub 4 and 5. Here's 4. Here's 5, right? And next is a plus b over 2. Or if you like, you can copy this. See, paste it here. Enter. And finally, equation 8. Equation 8 is this. Will be with the primes. 4 prime, 5 sub 5 prime, and x, and that's it. That is all the questions you have. Okay. I'm going to pause here just to wait you guys. Now let's finish this. Please shift enter. So you have these 8 equations. The math coefficients now, you see, the only thing you have to change this. So instead of 4, now we have 8 equations, and E goes 8. right? It has to be 8 and 8. The same, the rest is the same. There it is. Matrix form, you see, it has to be a matrix 8 by 8. And here, please, now here, mat 2, you have to only add this, comma, equals to LB. Like this. And we're going to plot the determinant. Now we have like this. Don't change anything, you see this. Okay. I'm going to check back again this, no problem. So I'm going to erase this because I don't need this. Now this is the roots here. Okay, I repeat again, please. Here, look what I'm doing here. Once you define the equations, you have 8 equations, you see? Here, the only thing you have to change here is this value. Here it was before 4, now it's 8. See? And the matrix form is you are going to get this, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. 8 by 8 matrix as we define. Since it's not possible to use analytical solutions, so we have to get some numerical matrix, and here is the numerical matrix, please. Just you have to add this value here. B goes to LB, you're going to have this. And finally, if you are able to plot this because you define this value. And there it is. Since we need to see the roots here, that's the reason we do this sum and here. How many roots has this, please? Has 2. Here there are 2, as you can see. If I do a sum here, I see there is 2. Here there are 2 solutions. 2, 4, 6. There are 6 solutions. If you do this, you're going to have 1, 2, 3, 4, 5, 6 solutions, please. And finally, we have to get these arbals. 6 solutions. Till here, please. Everyone here. I'm going to pause here.